Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome back to the second edition of Fundamentals of Solid Formulation webinar series. This is a 7-week webinar series with a webinar every Wednesday at 11 a.m. by a leading expert who understands your daily workflow and will share his or her real-world experience in successfully supporting preclinical and clinical projects in the industry. So, as you all know, we started the webinar series on April 7th, and we'll be ending it next week on May 19th. So far, we have had 5 leading experts from the industry sharing their expertise in solid formulations, starting with Dr. Henry Morrison from Gilead on April 7th, and followed by Dr. Sudhakar Garrett from Novartis, giving a webinar on April 14th. Then we had Dr. Luca Isolino from Merck, who spoke about CSP and solid-state modeling on April 21st. Then we had Dr. Daniel Joseph Price talking about amorphous formulations for solubility enhancement, risk, and opportunities from Millipore Sigma on April 28th. Then last week, we had Dr. Luca Russo from GSK sharing a current practice and future perspective in crystallography for API solid form risk management. So this 7-week webinar series is jointly organized by XLPI and JSTAR Research. XLPI is an algorithm-driven artificial intelligence-based pharmaceutical technology company with sites in Boston, Beijing, Shenzhen, and Shanghai. JSTAR Research is an innovative CRO based in New Jersey and is an independently managed subsidiary of Photon. Photon is a contract development and manufacturing organization based in China. The 3 organizations are strategic collaboration partners in pharmaceutical drug design and preclinical development programs. My name is Sivakumar Segran. I'm the Senior Director of Business Development at XLPI in Boston. I'm going to be your moderator today for the webinar series. And before we move on to today's webinar by Dr. Alesh Medek from Vertex, I just want to give you a brief recap of what happened in the last 5 weeks. So pretty much if you go to xlpi.com and click on the events page, under FSF 2021, you can see all the previous webinars recorded and the links are posted on our website. So if you just click on the play button next to the speaker's name, you'll be asked to fill in a form, which pretty much requires you to put in your name, affiliation, and email ID, and then you can watch the recordings. And also available along with the recordings is the Q&A page where questions that were not answered during the live session are answered by the speakers at a later date and also posted along with the recordings on our website. So pretty much everything is captured and made available to all the participants out there. So today we have Dr. Alesh Medek from Vertex joining in, and Alesh is a research fellow at Vertex, and he specializes in solid-state characterization of pharmaceutical solids with special interest in characterization of disorder. At Pfizer, Alesh built up global solid-state NMR capabilities and developed multitude of new solid-state NMR pharmaceutical applications. At Vertex, Alesh interest expanded from solid-state NMR to all solid-state characterization techniques. So today, he's going to talk about application of nitrogen solid-state NMR to differentiate and quantify different API amorphous phases in complex tablet formation. So before I pass on control to our speaker today, I'd just like to encourage all the participants to use the questions tab to send in your questions during the live session, and use the slide number to indicate which slide you're referring to so that the speaker has some additional time to take in more questions during the live Q&A session. So without further ado, let me hand over control to our speaker today. Over to you, Alesh.
All right, so first of all, I hope you can see my slide and cursor and you can hear me. Shiva, yes. Can you confirm? Excellent.
Yes, thank you.
So hello, everyone. Good morning, afternoon, evening, wherever you may be located. Well, first of all, I would like to thank the organizers, Crystal Pie, Shiva, and his team for putting together this wonderful webinar series, the lineup of the speaker, and this is already obviously second annual series. It's already going for a second year. I believe Shiva intends for it to continue further. Well, so before I get to my presentation, I should say that the the title of my as the title of my presentation suggests, we use solid state NMR as a tool to follow amorphization of crystalline API salt into amorphous salt, and the amorphous salt further disproportionating into amorphous freeform. And I'm going to explain how by quantifying, by differentiating, first of all, these two amorphous phases, and by quantifying them, we were able to de-risk important late-stage development project from chemical degradation liability. So couple of points. First of all, this was no academic exercise. I already mentioned this was a late-stage project. It was real-time project needs. We responded to, we had to develop the methods in real time, and the formulation was truly complex. So besides the common excipients like fillers, disintegrants, lubricants, and so on, and our API, there were other API present. So again, to wrap up, we were quantifying two amorphous phases of a API, the featured API, in the presence of other API and all the excipients in the tablet. Second of all, this is the first time, to my knowledge, this story sees the lights outside of Vertex. So, I'd be using the feedback from the audience to fine-tune the future manuscript. We are obviously in parallel working on writing up this story and publish it in a peer-reviewed journal. So I'm looking forward to the questions and feedback from the audience. And lastly, by watching the other speakers, my fellow webinar presenters from this series, I decided to broaden up my slides a little bit. Originally, this was really supposed to be focused on the main topic of the title, but I have decided to include like general education about solid state NMR and comparison of solid state NMR with other solid state techniques. So let's get going. So by the way of background, freeform of API has shown chemical degradation liability, and the chemists quickly found that the degradation could be mitigated by forming a salt. But the remaining problem to solve, or remaining question to answer, was how do we assess the risk of salt disproportionation to the free form upon the processing into tablets or during storage? Well, for that, we needed solid state tests, as we assume the speciation, the species, salt or free-form species of API might change upon the solution. So we couldn't use HPLC, for example. It had to be a solid state test. At the bottom is the acid-base reaction used to actually making the potassium salt. So the free acid in the presence of basic potassium hydroxide forms the salt. And of course, the question I'd be answering, or the task we were tasked, is to assess the risk of the reverse reaction. So during processing or storage, these potassium salt in the presence of now going the other direction, acidic excipients, what is the likelihood to fall back to free acid? And the free acid, by having this proton back, has the chemical degradation potential. All right, so I'm starting a little bit from the end. So giving you the clue that's because I want you to follow basically what we did and understand in real time what we did, rather than guess and wait to the end to give you the murder mystery ending. So I will keep some secret, till the end, but here is the outline. Here's the mechanism of disproportionation. So first, the crystalline potassium salt disorders to amorphous potassium salt. The amorphous salt disproportionates to amorphous freeform in the presence of acidic excipients. And the amorphous freeform, as well as crystalline freeform, show the chemical degradation liability. So I already mentioned that we have to use the solids test, and the solid test must be able to differentiate these crystalline forms at the minimum, or these forms, so not only crystalline, amorphous also. So the crystalline potassium salt itself, amorphous salt, when it amorphizes, then when it disproportionate to amorphous freeform, the amorphous freeform itself, and potentially even the crystalline freeform if the amorphous freeform crystallizes to crystalline freeform. And just, you already guessed that we're gonna use solid-state NMR from my title. So just to put it to perspective, of course, we tried pretty much all the arsenal of the solid-state technique, X-ray, vibrational, and so on. And they all had troubles differentiating the two amorphous phases, mostly even as pure drug substance, not even in the presence of the complex excipients and the other APIs in the formulation. So I should say that IR was at least successful to do it in drug substance. It could differentiate the salt from freeform, but it couldn't differentiate the crystalline phases from amorphous phases. So it could see salt from freeform, but it couldn't tell whether the salt is amorphous or crystalline or the freeform was amorphous or crystalline. And that all was scrambled when in formulation. So it can do it in drug substance, but not in formulation because IR used the carbonyl stretch, that was basically masked by other excipients and other API. All right, so after outlining this background, now I'm gonna give you a kind of crash course into solid-state NMR, just a few slides. I'm not gonna, this could be topic of several webinars by itself. So why might we need solid-state NMR? So on the left is the pharmaceutical application list, and it's by no means a complete exhaustive list. I'm not gonna even go over everything. I let you read it. Just a couple of highlights. Typical application is for polymorph ID and a couple of intellectual property, like similar to X-ray. I would argue that NMR is arguably better, because it usually has sharper peaks, so you can have better selection for the claims. And if you're lucky and your API has fluorine, for example, no other excipient has fluorine, and if for potential, so if you patent the fluorine NMR, and there is some future litigation, you can ask for the full formulation and still by fluorine detect only your API and prove that somebody is infringing on your patent. So I'm gonna skip to here, number of molecules per asymmetric unit. Just from the last week's seminar of Luca Russo from GSK, he showed how the Z prime can be derived very easily from basically counting the peaks in either fluorine, carbon, or other nitrogen solid-state NMR. So he used several case studies where he very nicely showed how this was done. I'm actually going to show you example on the crystal bound solvent and pure phase versus mixture. Hydrogen bonds and proton transfer is actually the feature story of these presentations. So we see quite a bit about that. And maybe stop here for a second. Distance measurements, domain sizes, and NMR crystallography. So again, Luca Russo last week showed several examples how to use carbon and nitrogen chemical shift and connect it with CASTEP, quantum mechanical calculation, and of course X-ray to do CSP, crystal structure prediction, to derive structures. Before I switch to the right side, to the advantages of, with respect to other technique, let me just say that, the gospel, that I'm talking about solid-state NMR, and I'm expert. I would consider myself expert in solid-state NMR, but we absolutely have to use all the techniques in parallel because they all have orthogonal. They allow for orthogonal information. So solid-state NMR and X-ray especially are very suited and provide complementary information. So I definitely advocate for all technique, even though I'm talking about solid-state NMR today. So what are the advantages of solid-state NMR? It's complex with compatible with complex formulation. Again, we will see that because it's built into the title story. very sensitive to polymer variation. There is very little sample prep. It's quantitative. I have special slide for it, so I will defer to that. No preferred orientation. Let me stop here and say that, yeah, unlike X-ray, it has no preferred orientation. I should say that in X-ray, the preferred orientation is, its origin is well known. It's oriented, the preferred oriented in the particles, and the solution is also well known, grinding. But as simple as it sounds, you never know, especially on new project, new samples, how little, how much grinding is necessary. Because if you grind too little, you're not going to remove the preferred orientation. If you grind too much, you will change the sample. You may change the form or even amorphize the sample. So, luckily enough, with the newest diffractometers having the 2D cameras, you can at least tell post-acquisition that you might have preferred orientation by seeing the spotting in the diffuse diffractive rings, basically. So at least you can tell if you have the 2D detectors. All right, let's move on. This is basically my only true theory slide, and I decided to include it because of the NMR crystallography. So I already mentioned that Luca used last week the chemical shift information and only the chemical shift information and calculated the chemical shift. But there is a whole universe of other possible constraints for NMR crystallography. The most important are actually distances. So NMR can actually very precisely measure distances. And it's through these so-called dipole-dipole coupling. So the NMR nuclei, for example, these two protons do behave like magnets. These coupling, dipole coupling, has orientation dependent, and of course, what we want is also distance dependent. So the little tidbit of information, I'm assuming that pretty much everybody in audience know liquids NMR. So in liquids, these dipole-dipole coupling averages to zero basically by fast tumbling of molecules. So you cannot observe it directly. So you cannot measure directly distances in liquids. But you may know that you do actually use so-called NOE or nuclear Oberhauser effect, which is basically cross relaxation based on dipole coupling. So it's proportional to this dipole coupling square, or 1 over R6. So you can measure distances in solution, but indirectly. So this dipole coupling can be homonuclear, like shown here in protons, but it could be heteronuclear, like proton, carbon, nitrogen, and so on. And again, you can measure very precisely the heteronuclear distances and use those as a constraint. Or you can use the effect of so-called spin diffusion. So basically, any organic molecules have abundance of protons, so they work like a network of connected, basically, magnets through the dipole coupling. And any property you will measure, like for example, relaxation, will be averaged to the same value. So unlike in solution, where each of these protons can have different relaxation, in solid state, because of the dipole coupling, they have the same value. And I will show you a couple of slides later how this could be useful. Of course, we can measure directly the spin diffusion type, the spin diffusion, and get a distance out of it. If we can know the diffusion coefficient, we can measure the diffusion coefficient on a compound with known distances. So we can calibrate basically these and then just measure time and get the distance. So yeah, distance measurement is a big thing for an MR, and actually in at least favorable cases, structures can be solved solely from an MR. But again, I cannot overstress combination of techniques, and absolutely powder X-ray, solid state MR to solve structures. All right, a little bit on sample sizes, holders, and so on. You may have heard about magic angle spinning. Well, there is no magic in magic angle spinning. It's actually, the term itself was not even invented by solid state NMR spectroscopists. It's a mathematical term. You basically, if you look at this cartoon, it's the angle between the diagonal and any of the cube diagonal and any of its sides. So if you think of this axis system, you start rotating the cube 90 degrees at a time along the diagonal, you will switch the axis, and if you do it fast enough, you sort of equalize the space. So this is like a rough, understanding of how magic angle spinning works. And it's used to basically remove the anisotropies in part, like the dipole coupling, chemical ship anisotropy, and so on, to get sharper lines. Well, as far as sample holders, we have variety of sample holders. This is definitely, again, not a complete list. If we want the highest sensitivity, we use this biggest rotor, which can take up to almost 300 mix. But the downside is a relatively slow maximum spinning speed, so quality of spectra. Of course, on the other side of the spectrum, this slide is, by the way, more than a decade old. So in early 2000, this was the rotor with maximum spinning speed. Nowadays, the record, I don't even know, but I believe it's reaching, if not already, at 200 kilohertz. So it's amazing. And the rotor size is much smaller. The OD is much smaller. External diameter is much smaller than 1 millimeter. It's 0.7 or even maybe even smaller. It's very good for proteins where you have less than milligram things, so you can fill the small rotors with. So at least at Vertex, we use the kind of Goldilocks, what I like to call Goldilocks type of size and maximum spinning speed. So we use the 4 millimeter rotor, which takes about 70 microns of sample. All right, so this slide is quite important for understanding the feature story. So let me go relatively carefully through it. So quantification by magic angle spinning versus cross-polarization magic angle spinning. So magic angle spinning is very simple. As I showed on previous slides, you basically orient your rotor and magic angle, spin it as fast as possible. And as far as the pulse sequence, again, as simple as it goes, 90-degree pulse acquisition with optional decoupling. Well, it's used for abundant nuclei like fluorine, phosphorus, or protons, because abundant means 100% natural abundance with high sensitivity. We can also use them for so-called quadrupolar nuclei like bromine, sodium, chlorine, deuterium, or boron. It affords, from the first principles, quantitative peak intensities. So basically, if you integrate the peaks, the peak intensity ratio, the area under the curve ratio will be the molar ratio of the species, basically, from first principles. No calibration mixtures necessary. So whereas cross-polarization magic angle spinning is basically signal enhancing technique. So the signal literally starts at protons and is cross-polarized in this cross-polarization step to the rare nucleus, carbon or nitrogen, and it's detected with, again, optional decoupling. Well, it affords two sensitivity factor. One is the so-called gyro nuclear ratio between proton and carbon, which is enhancement factor of 4 times, or for nitrogen 10 times. But because I should say also because the signal starts at protons, it's the proton relaxation that determines the recycle delay between the subsequent scans, not the carbon or nitrogen relaxation, which is typically much longer because it's dipole based and they are less effective dipole. The relaxation is dipole based. And well, I should say that there is no free lunch. The price to pay for this sensitivity or increase of sensitivity is non-quantitative peak intensities. But why so? It's because of the cross-polarization step. So the cross-polarization itself depends on the dipole coupling I just described. And because it depends on dipole coupling, it depends on the distances between protons and the carbon, nitrogen, and it also depends on the local mobility of the molecule. All right, let's get moving. Just, I believe, like 3 slides of quick examples, which I think are very important. So this is on distinguishing solvent occlusions versus solvent with defects versus phase-separated solvated phases or solvates. So this is actually very simple but powerful application. this is all based on proton spectrum, and you can get proton spectrum usually in seconds. So we, on every single sample, we always acquire protons, so you get this information for free, basically. So let me start on the bottom right here. So what we see is this broad solid state API proton spectrum, and with like these two sharp peaks, which happen to be liquid, and the liquid is MTBE, methyl terbutyl ether solvent in this case. You can see that it's very characteristic. It's the sharp lines basically stick out from the broad solid state background, like the short term. It's you can quantify them very, you can integrate them, so you can know how much liquid you can have, and it's very sensitive. Usually 0.01% or so, 100 ppm, maybe even lower, is the limit of detection here. If we combine this information from size NMR to TGA and DSC, in this case, we saw by TGA and DSC that the compound released 0.9% MTBE at the melting point of the crystal. So if we couple these two information, we see liquid in NMR. And I should say, if we look also at carbon, fluorine spectra, you can search for liquid peaks, the solvent peaks in the carbon spectra. Let me briefly flash back what I forgot to mention. Because of the dipole coupling based cross polarization, anything you detect by CPMAS is by definition solid state. Remember, I told you that the dipole coupling is average out to 0. So if you have mixture of solids and liquids, by CPMAS you see only the solids. So again, in this scenario, if the sample was wet by itself and you look at the carbon NMR, you should, the CPMAS carbon NMR, you should see only the solid portion, and you would see if you have any solvent present as a solvate. So altogether, in this scenario, in this case, it wasn't the case, we concluded that MTBE was present only in occlusion. So the first case, solvent occlusion. At the top, we see in this example, there are no sharp liquid peaks in proton NMR, but again, by DSC and TGA, there was a release of 0.23% IPA upon crystal melting, and we didn't see any solvated phase by the carbon or NMR as I described. So the only conclusion was the IPA was present as crystal defects, usually in solid state in one phase. Usually you don't see by carbon, you don't see defects because they are basically amorphous and they are located under the main peaks. So you cannot see them directly, typically. All right, I mentioned that already that you can use relaxation as a simple tag to distinguish pure phases from mixtures, and this is how you do it. So here was kind of like testing mixture. So I already labeled the peaks. This is fluorine and MR. So we had form A and form B. And so imagine if you didn't see the labels and just acquired proton relaxation by this simple technique, fluorine observe proton relaxation experiment. It's basically very sensitive. So again, it can be done in minutes or less. If you measure the proton relaxation and compare the nodes, you can see that these two numbers are within experimental error the same, and these two numbers are the same. So you would conclude that without seeing the labels or knowing anything about your sample, that you have very likely mixtures of two compounds, each with 2 molecules per symmetric unit. If you knew that there's only one fluorine in the molecule, of course, there could be 2 fluorines, and then you would have to know at least the structure to conclude that. All right, if for some reason, if you are being unlucky and the relaxation might be coincidentally the same, you can still, or if you need, to confirmation that was the case, you can use 2D correlations where, like in this case, the appearance of the cross peak only can mean only one thing, that the two fluorines in questions are close spatially on the molecular level to each other. So in this case, again, it's two molecules per symmetric unit. It cannot be a mixture. And on the right side, this is, flashing back. This is exactly the same sample as shown here in a 2D mode. And we can see, at least for the form B, the cross peaks, that is small cross peaks for the form A. This is because it was done with relatively inefficient double cross-polarization sequence. And I definitely need to mention that the acknowledgement, the credit goes to Pfizer. So these slides are more than a decade old, and they were clear by Pfizer at the time for external presentation. I just, when I broadened up my slides, I just couldn't find some Vertex approved equivalent. I can assure you we do it pretty much every day. So just didn't have the clear slides to show you. So nowadays, actually at Vertex, I'm sure other, elsewhere, everybody is using more efficient sequences like these dipole-assisted rotational resonance, or DAR, that would definitely on these mixtures show all the cross peaks. All right, getting back to, hopefully I'm doing well on time here. Getting back to my feature story. So again, just to remind you, we need to differentiate two amorphous phases in the presence of their crystalline equivalents. So by what I told you by now, it shouldn't come as a shock that we use fluorine as a first line of defense because it's fully selective, doesn't, no excipients have fluorine, it's fully quantitative, 100% natural abundance, has good resolution. But if you look at this overlay of the reference forms, we can see that there is very good resolution of the crystalline form, crystalline salt and crystalline free form. There is even decent resolution between either of the crystalline form and the amorphous phases, but there is really poor or no resolution between the two amorphous phases. So the natural next step was to look at nitrogen, because we know that nitrogen has exquisite sensitivity to detect protonation, and the point of protonation in this salt was right under nitrogen. And I should point out that, again, back in my Pfizer time, in 2006, we actually published on using solid-state proton NMR to distinguish proton transfer and to differentiate co-crystals from salts. And maybe as a tidbit of information, one of my Pfizer co-authors at the time was Yuri Abramov, whom many of you may know is computational scientist and is happily employed by no other than Crystal Pi in presence. So back to the nitrogen, sure enough, we've been able to actually resolve the amorphous phases. There is almost baseline resolution. So, that was a good thing, obviously. So going forward. So issues and mitigation of nitrogen, solid-state NMR, low sensitivity due to low natural abundance. The mitigation, at least for research samples, obviously, was enrichment. We cannot enrich production samples, but if you want to understand mechanism, you have enrichment as a research tool, obviously. And because it's a low abundance nucleus, you have to use CPMAS method. And I already explained CPMAS peaks intensities are not quantitative. So the mitigation was calibration based on reference mixtures. So first step was actually to prepare the N15 labeled analogs of form analogs of the unlabeled samples. So we synthesized them, and we had to confirm that they are the same as the unlabeled species. And so these are actually fluorine spectra of unlabeled, as well as fluorine spectra here of the labeled forms, and they were identical. So we confirmed we made the right forms. Then we started to make the mixtures in order to calibrate our quantification. So I'm showing two of these calibration mixtures, 50-50 amorphous mixture of both amorphous forms, and 45-45-10, with the 10 being the crystalline salt. And basically what we did is, again, integrate the area under the peak of the amorphous freeform as well as the salt in the mixture. And the interesting thing you can notice is that even though this is 50-50 mixture, the area under curves are very different. The amorphous salt one is about 6 times smaller than that of the freeform. How is that? So again, it goes back to the CPMAS. And in this particular case, because in a free form, the proton, the CPMAS signal starts from, is attached directly to the nitrogen. So the transfer is very efficient. We have good intensity. Whereas in the salt, the closest protons are buried further away in these R2 and R1 substituents. So the transfer is inefficient. But that actually serves very well to our purpose. Remember, we have crystalline salt in a tablet. That's the main component. That's what we want to have there, which amorphizes to this amorphous salt first. The only fraction of the crystalline salt amorphizes, and then a fraction of this amorphous salt disproportionates to amorphous freeform. So having 6 times more sensitive method to detect the freeform is actually boon. It's actually very welcome. So we got lucky here. All right, so then we put these nitrogen labeled prototype tablets on stress conditions, highly stress conditions, 70, 75, and follow them up to 3 weeks. And we watch the amorphous salt portion as well as the amorphous freeform grow. And before I show you the quantification, the result of the quantification, here is how we actually did it. So we could have used the relative response factors from the nitrogen spectrum between the crystalline component and both of the amorphous, but we decided to use fluorine to quantify the total amount of amorphous phase, because fluorine is inherently quantitative and it's very sensitive. So we thought it would be more accurate. So that's what we did. So on this particular example of the sample stress for 4 days at 70, 75, we found about 17% of amorphous phase, and then use nitrogen CPMAS on this labeled sample to basically proportionate the 17% between the two phases. So again, if you integrate the amorphous salt, the AUC is 24, the AUC of the amorphous freeform is 23, then by using the relative response factor, we can correct one of the AUCs, which is here, and then that gives us the final true ratio, quantitative ratio of the two amorphous phases. So here's the quantification itself. So it increases and it seems to plateau, over the time, close to the 3 weeks, it's almost plateaued. You may ask, why is that? And I'm coming back to the mechanism now. So I will show you the revisited mechanism on the next slide. But I told you that the drug has to amorphize first, and the crystalline salt is actually the most stable form. So you may have wondered, how is it that the most stable form amorphizes? So here is the answer, really. So what's happening is when we stress it at these highly stressed conditions, basically the crystalline drug dissolves in the polymer that is present in this complex formulation. And the plateauing here means that basically it reached the miscibility limit with the polymer. Also, if you have keen eye, you can notice that the amorphization actually doesn't start from 0. There is a very simple explanation for this, and it is that when you compress these tablets, you actually create a little bit of amorphous phase, about 4% in this case, by the shear compression, so by the pressure, by putting defects into the crystalline phase, part of it amorphizes just by compression. All right, here is the promised mechanism of disproportionation. I'm almost at the end of my talk. So the crystalline API dissolves into the polymer above the polymer TG. So in the polymer molten state or rubbery state, if you want, to form amorphous salt. So that's the mechanism of amorphization of the stable crystalline salt. Then this amorphous salt reacts with HPMCAS, hydroxypropyl methyl cellulose acetyl succinate polymer of the complex formulation, actually with this acidic moiety of the HPMCAS succinyl moiety to form the free form. And the free form, by virtue of having this hydrogen back, is susceptible to chemical degradation. So you may ask, how do we really know that the crystalline API dissolves of the polymer, and how do we know that it's this HPMCAS that drives the acid-base reaction? So that I'm gonna show you, give you proof on the final next two slides before wrapping up. So this is how we know that the crystalline salt really dissolves into polymer. We use this unlabeled drug product and use fluorine NMR to quantify the total amount of amorphous phase, which is plotted here. So this is time and total amount of amorphous content at these different stress conditions. Again, these are unlabeled drug. Those are the authentic late stage development drug products, stress at these conditions. So interestingly, if we put it in perspective versus TG of that polymer in the mixture, we can see that there is very good correlation of being above the TG, the rate of amorphization, or the amount and the rate of amorphization increases. And I'm not showing it here, but of course we stressed below the TG of the polymer and we didn't see any amorphization. And again, we don't start from zero because it's the same thing, we create some amorphous form in the authentic tablet by just compression of the tablet. So that explained why that really gave up that the crystalline salt is dissolving into our polymer. So how did we know that it was the HPMCAS that was the culprit in the acid-base reaction? Well, we simply remove it. We guessed it and then remove it from the formulation and watch what happened. There is still another polymer. Remember, it's a complex multiple active combo. So there was yet another polymer the crystalline salt could dissolve into. So here's the example on this HPMCAS-free tablet at 2.5 days in green and 4 days in black. And we could see roughly the same amount of amorphous salt present, but at 4 days there was about equal intensity peak for the free form, whereas here, after removal of HPMCAS, we don't see any free form forming, so there was no disproportionation, proof that that it was HPMCAS driving the acid-base reaction. And to conclude, I hope that I show you enough evidence that the nitrogen NMR can be very useful by, in this case, confirming the disproportionation in drug product, quantifying both amorphous salt and free form, confirming the mechanism of disproportionation, and it suggested a mitigation strategy to avoid chemical degradation liability. I haven't mentioned it, but the mitigation strategy was very simple. Avoid stressing these tablets over the TG of the lowest TG polymer in the mixture. So finally, I would like to acknowledge my Vertex colleagues. It was a big team. Of course, it was late-stage development project. So basically, majority of Vertex people work on it one way or another. But on this particular analytical issue, those were the colleagues involved. And I would like to again thank the organizers, Crystal Pi, and you, audience, for bearing with me. And I'd be very happy to entertain any questions. Thank you.
Thank you, Alish. That was a wonderful presentation and a lot of very useful information for people working with solid state NMR techniques. So really appreciate your contribution to the webinar series. Let's move on to the Q&A session. The first question is related to slide 4. In fact, we have 3 questions related to slide 4.
Okay, I'm jumping in. Bear with me. All right. So now we should hopefully see slide 4.
Yes, but
Okay.
not sure if this is the slide they're referring to, but anyways.
Okay.
The question is, can solid state NMR differentiate physically bound solvent and lattice solvent?
All right. So that was probably more question for this slide. So physically bound solvent would be the liquids case, though not in occlusion. Well, but I'm assuming physically bound meaning surface bound. So it would be considered phase separated liquid, and you would see these sharp peaks. Whereas if it was lattice bound, that's what I exactly mean by the solvate. So yes, that would be the case that is the remaining case that is not shown here. You would have to use you wouldn't see the liquid in proton NMR, but you would see phase separated sets of peaks, including the solvent itself in carbon and or fluorine, nitrogen, and so on. So absolutely, it's one of the strengths of the solid state NMR.
Okay.
I'm gonna go back to slide 4.
Yeah. The next question is, to what extent does a typical impurity would affect or impact the accuracy of your analysis?
I would say to no extent. NMR is that's the biggest strength, that it's compatible with complex formulation, including impurity, excipients, and so on. Fluorine, for example, again, is not impacted by anything else not having fluorine. So, I mean, if the order of the question has some specific example, I could go deeper, but in general, pretty much not affected at all.
Okay. Then I think probably you might have answered it during your presentation, but anyways, the question is, can nitrogen NMR distinguish salt and co-crystal?
Yes, so
Okay.
I could flash the publication again. Let me do that actually. So that was the topic of this publication.
Okay. Okay. Great. Could you move on to slide 14, 1-4?
Yep.
The question is, the amorphous salt and free form spectra are similar, but then in slide 15, the two spectra are different. Could you
Okay.
explain that?
Absolutely. So I apologize, it's the axis label. So what's shown here is fluorine spectra of these forms on unlabeled samples in the bottom and 15 labeled at the top. We just use the fluorine to show that we made the right forms. Then on the next slide, I'm showing the nitrogen spectrum of these. I forgot the,
Okay.
yeah. Hopefully I explain it.
Yes. Thank you.
Here, this is probably the author referred more to this slide. How is the bottom and the top different? Bottom is the fluorine, top is the nitrogen spectrum.
Correct. Okay. Thank you. The next question is slide 16.
Oops, come on. I'm getting some problem in, okay, now it starts moving, good. So 16,
Okay.
yes.
Yes. Was DSC used to differentiate the amorphous salt and free form after stressed conditions?
DSC used to differentiate amorphous form and that. So DSC may do that on pure drug substance. So again, these are prototype tablets with all the excipients and all the different APIs there. So there is absolutely no way that DSC can differentiate it in these very complex matrix. We have several polymers which are amorphous. We have several APIs that are amorphous. We have crystalline API, we have crystalline excipients, amorphous excipients, and so on. So DSC is the worst technique actually to differentiate these in these complex matrices.
Okay. The next question is, what is leading to the asymmetry of the fluorine 19 crystalline peak on slide 12?
It's a
Or maybe
very good
slide 4.
question. These, I'm guessing.
Yeah.
The short answer is I don't know. I can give you my guess, obviously. amorphous doesn't mean completely disordered. There is still some distribution of states that some of them are more likely than others. So there is lower distribution of T state than obviously D state. Typically, we see like in these fluorine more like Gaussian-like distribution, but asymmetric distribution is not unexpected. But why exactly this, I cannot give you a specific answer. This generic one that it's not unusual to see asymmetric distribution. It all depends on the mixture of states forming. Every molecule has slightly different conformation or orientation in this amorphous phase. So it's the distribution of these conformations that gives you this line shape, and the distribution must be asymmetric for some reason.
And what about the crystalline free base form?
Crystalline free base form, the asymmetry. So the same thing. Or these one, or these maybe. So that's a very good question too. And again, I don't have very good answer, but I believe this project was actually done 2 years ago. So I'm grasping my memory, but I believe that this particular free form was not quote unquote true form. It was dissolvated solvate. So again, there was some distribution. I might be wrong. I'm assuming that this was dissolvate. Of course, I can confirm and come back, but I believe
Sure.
that was because of that.
Sure. Yeah, we can answer that later and post on the website as well once you have some more information on that. Let's move on to the next question. Can solid-state NMR differentiate rotamers and quantify the ratio in the crystalline solids? Any required molecular properties or sample properties?
Right. So the short answer is yes, but you have to catch them. So um, we have freedom to change temperature, so you can freeze the rotamers. So if they are dynamic, you will see the average. If you freeze, if you can distinguish two rotamers, at given temperature because they are quasi-static, then you will see two sets of peaks basically, and you can distinguish. There is no specific condition or sample prep or anything. You just play with the temperature. If they are semi-static at room temperature, you will see them then, or you can heat up or cool down, depending on both, depending on mobility of those rotamers.
Okay. The next question is, which mathematical model you propose or suggest to predict the stability of a formulated solid based on nitrogen solid-state NMR measurements?
Which mathematical model? So first of all, you can use any NMR. I would prefer fluorine if fluorine has the resolution, between the species, because it has the sensitivity and selectivity you usually need, and it's quantitative. But you can use carbon, fluorine, nitrogen. It doesn't matter. And as far as the model, I'm assuming that you're talking about stress crystallization of amorphous phases, so you're following the crystallization. There are multiple models you can follow. Usually we do it in-house by trying to see the nucleation onset and growth for early crystallization and fit Arrhenius, do it as a function of temperature, obviously, at multiple temperatures, and extend the Arrhenius fit to predict ambient condition behavior. I actually gave a few years ago a webinar just on that, so it would be it's a discussion for hours really if we were to go to details.
Okay, let's move on to slide 20. What is T? Is it a storage temperature you're referring to?
Yes. So yes, it's this temperature, and TG is obviously glass temperature of the polymer. So yeah, T is 80C in this case, 70C in this case, and so on.
Okay, staying on slide 20, another question. Did free amorphous forms start a chain reaction for amorphous salt disproportionation without any additional stress?
Did free form start the chain reaction? So I guess the question is about the nature of the chemical degradation. So I'm really not a chemist. I just know that when you have the free form, when you have the proton, maybe I can say that the degradation reaction itself was internally known by these very um, uh, very scientifically rigorous name called Fall-Apart reaction. The molecule literally fell apart at the place of the nitrogen, basically. I don't know if that answer, maybe I'm answering different questions, but that's how I understood the question.
And not sure if you can answer this question, but anyway, I'll go ahead and ask this. It comes from a participant asking, was this amorphous solid dispersion, and could you disclose the name of the drug?
I rather not disclose the drug
Okay.
or the amorphous dispersion. Sorry.
Okay. Next is slide 19. Without polymer, the crystalline API does not transform to amorphous salt. Do you agree or disagree?
That's correct. That's very correct understanding. Yeah, the potassium salt was the most stable form of the potassium salt, which by definition is the stable, but it does dissolve into polymer in the rubbery state of the polymer.
Okay. Another question, as a follow-up to the amorphous quantification, in particular the salt disproportionation, where orthogonal analytical techniques explode, namely metal analysis or for potassium content or XRF, ICP-MS, etc., to complement the solid state NMR data.
Right. So we haven't looked. I would have to think about it a little bit more before giving, authoritative answer. But I guess by any, there is nothing changing with respect to composition of the system. So there is the same amount of potassium potassium moles basically in the system. They just change hands, kind of. So you have to detect the species correctly in a solid state. So if there are other techniques capable of doing it, yes, by all means, they can be used.
Okay, time for two more questions. So the next question is, what is F species? Are you referring to CF3 or just CF?
F species, I'm not sure where it's it was speciation by fluorine, probably, if F species were on my slide. And yeah, these compounds have CF3 group, so that would be correct. It would be CF3 in that case. Yes.
Okay, great. Last question for today's Q&A session. This is related to slide 12. I think maybe you have already answered it, but anyways, let me take it. There is a difference in the chemical shift between the amorphous and crystalline form. How could this difference be rationalized in a chemical change?
So I mentioned it a little bit, or yes. So nitrogen is extremely sensitive to its protonation state. So this is again nitrogen NMR, nitrogen spectra. So depending on whether you have hydrogen on the nitrogen or have salt which doesn't have the hydrogen here, NMR chemical shift changes dramatically. You can clearly see it here. That's how we resolve it. And again, I could point the author of the question to perhaps these papers and others. Obviously, it's not the only paper on N50 solid state NMR out there. So
okay.
If this was the last question, I would still take the opportunity to thank the organizers, Shiva, you, and the Crystal Pi team, and as well as the audience for attending the presentation, bearing with the presenters, bearing with me today. Thank you very much.
Thank you, Alish, for the wonderful presentation. And yes, we have answered all the questions that we got during the live session today. So there are pretty much no pending questions from the audience. And once again, it's a wonderful contribution by Dr. Alish Medak. Just wanted to mention to the audience that Alish is one of the essential employees of Vertex, so he has to be in the lab almost every day. So for him to take the time today and give this presentation, we really appreciate his wonderful contribution to this 7-week webinar series. Thank you, Alesh. Really appreciate it. And so what's coming up next week? That's pretty much the last talk of this 7-week webinar series. We have Dr. Adam Keats from Syngenta. Adam is a specialist particle scientist at Syngenta in UK, and Adam is part of the process studies group working on polymorph discovery for new active ingredients, finding new ways to crystallize and predict polymorphs and understand the influence on formulation. Adam will present unique challenges in crystallization related to the agrochemical industry, where there are a range of formulation types, and the desired solid state is driven by formulation stability, which can result in complex mixtures of solid forms. The title of Adam's talk is Crystallization in Agrochemicals, the Good, the Bad, and the Unusual. So looking forward to Adam's presentation next week, and also the end of the FSF 2021 webinar series next week. So once again, I'd like to thank all the participants for tuning in today and listening to Dr. Alesh Merek's presentation. Please feel free to reach out to us with your comments, questions, and once again, it's all about you, not about the organizers. So one of you could be a speaker for the next series. So reach out to us with your topics or anything that you could contribute to this webinar series, and we'll happy to take that forward. So thank you very much for your attention today, and looking forward to seeing you next week. Until then, take care, stay safe.